Assalamu alaikum. My name is Amber, and the topic that I have for the talk prepared is N is better than 1. So it's more related to the parallel computing that is provided to us by Python. So I want the session to be interactive, so I'll be asking questions around just to keep you guys awake. So let's just begin. Currently, I'm working as a data. And if you need to contact me after this presentation, so here is my email. Okay, so the agenda is that first we're going to start with what and why do we need parallelism. Next, we're going to see what's the difference between concurrency and parallelism, if any. And then we're going to discuss the input, output, and CPU-bound processes and how can we parallelize them. And lastly, we're going to reach a conclusion based on all of the discussion that we're going to have. Okay, so for now, I would like all of you guys to think yourself as a miner and one of your fellow friends. So the task at hand that you're provided is that you are to dig a hole and you're to find diamonds. So there could be two strategies as to do this. So the very first is that you can take turns digging the hole. So there could be miner 1, and then we can have a miner 2, that might be your friend. So if you take turns digging, so in an ideal world scenario, it probably takes around 100 minutes in order for you to do that. But can anybody in the audience tell me that what an alternate strategy to this might be? By the show of hands. Raise your hand if you can use the mic.
They can use parallelism.
Yeah, that is, I think, we know that it's implied. Okay, so they can do it parallelly, that is, if both of them, they work on the same problem and they're digging it together, so they can reduce the time by around half. So that is in an ideal world scenario. That doesn't happen a lot. So let's just, by this, talk about what is parallelism. So they're doing this thing in parallel, that is, they're doing it simultaneously. So in parallelism, we have an execution of simultaneous tasks, and that is provided to multiprocessors. So if we break down a complex problem into some easier problem, and then we drop it down on all of the processes in order for them to compute. So this reduces the time, and it reduces our computational resources as well. So you can see as the diagram over here, we have a sequential programming, and then we have some parallel programming. So in sequentially, we have task 1, we get the results out of the task, then a task 2 is given to the computer in order to compute on that. We get the result for that, and so on and so forth. But in parallelism, we have multiple problems at the same time on which our computer computes and gives us the result. Okay, so next I'm going to discuss that what's the difference between concurrency and parallelism. So how many of you know that they're different? Okay, and can anyone tell me the difference? Okay, so by this diagram, I think it's very clear that in parallelism, we have different tasks, but they're not being executed at the same time. They're being executed alternatively. But it's the process is really in a speed, so we get the illusion that it's being computed in parallel. But parallelism actually is that when you use all of those beautiful cores that we have, and we say that we have octa cores, or we have quad core, and we use those processes in order for the tasks to get executed. So by the English definition, we know that concurrency means simultaneous occurrence. But that's just not the case with Python. The things in concurrency, they're not being executed simultaneously. But multiprocessing provides us with this capability in order to process things in parallel. So in concurrency type, we have one preemptive multitasking, and the other that we have is cooperative multitasking. So both of these, they provide us with concurrency. That is that they're not being executed at the same time, but they're being executed alternatively. So we have multiple threads, and we have multiple tasks that could be executed at the same time. So the difference between preemptive multitasking and the difference between cooperative is that In preemptive multitasking, the operating system is actually the head of everything. So the operating system is basically our boss. And he can swap anything out or in whenever it feels like. So we have the number of processors that we have in the preemptive multitasking is 1. But that in cooperative, you do also have 1 processor. But in that, we are actually the boss or head of our own code, and we tell the operating system when are we done programming or when we are done coding, and then the task could be swapped out. But in a multiprocessing version, so all of the cores that we have, they get used up. So we have multiple numbers of processor in this problem, and the processes, all of these, they run on the same time, and different tasks are on these processes which are being executed at the same time. So the tasks that we can parallelize are input and output bound processes and CPU bound processes. So the input and output bound processes are the ones in which some external resources are involved. So the blue box that you can see in the diagram behind, it's actually the task or the work that is being computed onto your CPU. And the red ones are the things that we are waiting for some external resource to respond, so some input or output devices included into this. So how many of you face problem with your internet, the speed and everything? So it slows your processes down, and I know that is very disturbing, and it makes you upset and angry. So that is the network connection or file system. Whenever that's into our code, that slows our system down. So that's something that we need to work upon. And in the CPU-bound processes, they are slow if your CPU is slow. So there's no other way you can speed them up in terms of hardware rather than just change your CPU, but in terms of coding, you can do that. So we're going to see that how can we parallelize the input and output bound processes first, and then we're going to jump on to the CPU bound processes. So for these, Python provides us with threading, multi-threading, and we also have async IO, and then we have multi-processing libraries in order to fasten our codes. So the very first, I'm going to show you the synchronous version. This is a code over here. What this code actually do is download some content from the URL provided and prints the size of the content that it has downloaded. So I have a list over here, it's times 80, that means there are around 160 links which are to be downloaded and displayed. And in the main, I've displayed the time that it takes for it to work. The execution time is displayed on the screen as well. So in the download site, you can see that it's pretty much taking the session and getting the content and just printing it out. And in download all sites, we are looping through all of the URLs, and then we are getting the content for that. But to be keep in mind, the session that we have is 1 over here. So I'm sorry, Ali Asad, I'll just have to say that on my machine, it takes around 14 point something seconds, but it could take some less time or more time depending upon the network connection speed that you have. Since that's the external resource our computer is interacting with, our code is interacting with. So we can speed it up by threading. So how do we introduce threading is that the main is same, so I have not shown it over here. So over here, we have download site. So in download site, we are, in download all site, we have concurrent .futures.thread pool executor. So if I divide this into 3 parts, the thread pool executor is now creating a pool of threads, and its executor is basically controlling how these threads are being executed. And in the parameters, I have said that the max workers is equals to 5. That means that the number of optimal threads which are giving me the speed over here are 5. So we can play around with that as well. Now, there's a function called map in which it takes 2 parameters. We have download site over here, which is the function on which I want the sites list to be mapped to. So instead of a complete loop over here, you can just write one function and you're good to go. So over here you can see that instead of a simple request session, I'm also using threading local. So that's because threads, they use shared memory. So in order to avoid race conditions, we need to make threading.local over here. So each thread now has its own session and in which they can work around with. So this has actually speed up things quite a great deal. So the time that I'm getting is 3.72 seconds. So the pros are that it is fast, but the cons are that it is complex and it can also introduce some race conditions. How many of you know what race conditions are? So that's a problem with threading. So by this diagram, you can see that now, instead of waiting for the request from the external source, our threadings are now overlapping. That is, our CPU is not idle anymore. It actually has some work to do. So up next, we have the async IO version. And an async IO version is actually a lot of complex code rather than the threading. So over here, you can see that, okay, before I jump onto the async IO version, I'd like to tell you that we have another concept when it comes to async IO. There is a Python object called event loop, and we tell that when do we want to give control back to the event loop, so because there is no interruption in our code. So it is faster than threading. Moreover, it takes less resources, and another pro to it is that it doesn't have race conditions, because all of our processes, they are now being run on one thread. So previously, we had max workers, and I was telling it to be 5 because that was giving me an optimal result. Now in async IO version, it's quite scalable. So if I have one task per download, that won't affect my download time at all. Okay, so up next we have the multiprocessing version. Multiprocessing version is quite similar to that of the threading. So I have a pool of processes over here, and I set a global session because we have different memory spaces. So in order for the data to flow, we need to have a global session. Now you see that it gives me a time which is 5.7 something. So can anyone tell me that why it is increased instead of being decreased? We are using multiple cores. We are fully utilizing our processing power, but still it's giving an increased time rather than threading in async IO. Yes?
It could be dispatching at the same time, at which point you're running IO constraint.
Yeah, but one other thing is that in multiprocessing, we're using the cores, and the time that is being taken in the input-output processes, it's actually we overlap that time. So by the requests. So it's actually increased because these are heavyweight processes as compared to threads and as compared to async IO. So more of the resources are being utilized over here. So overhead is quite a lot. The communication overhead is as well. It's quite a lot. So but it works for the right problem, and we're going to see that what that right problem is. So coming to the CPU-bound processes. So in the CPU-bound processes, I have a straight linear code, sequential code, in which I'm just returning the sum of the squares of number which range from 0 to whatever particular range you provided to. So this version runs around 7.83 for seconds. Now can anyone tell me that what will be the effect of threading or async IO for this synchronous version? Will it increase the time, decrease the time, will have no effect? So how many of you say that this will increase the time? Okay, I have one. How many of you say that it will have no effect? Okay, and how many of you will say that it will decrease the time? Okay, so Ali is the winner over here. It will increase the time, and the fact is that because we saw that in the CPU-bound processes, we were spending no time in the input and output waiting. So there is nothing to be overlapped. So that is why the time that it is giving with threading is quite increased. So it's 10.4, whereas the synchronous version was 7 point something. So if you have a CPU-bound problem and you're using threading or you're using async IO for that. So it's basically all of that hard work is for nothing. So you're just wasting your time for that. So, but this is the multiprocessing version for this code, and for that, you see that the time has degraded a lot to 2.5 seconds. So to sum up all of this, in an input-bound process, in the synchronous version, it takes about 14.2 seconds. In threading version, 3.7. Async IO gives 2.5. Multi-processing version is 5.7. So if you have an input-output bound process, I suggest they use async IO version in order to speed up the things rather than going for threading version or the synchronous or the multi-processing version. And if we have in a CPU-bound process, you see that the multi-processing has degraded the execution time by quite a lot. So let me just conclude by saying that concurrency, it is complex because from the beginning we are just taught to how our code run in a linear fashion. That is, we're told that in the interpreter, whenever we code, so all of the code is being executed line by line. So thinking in terms of parallel could be difficult. But we need to know about performance issues if we want to make it parallel, and determine the type. So we also need to determine the type of process. Where do we need to use the CPU-bound processes? What type of multi parallel programming do we require for CPU-bound processes? What do we require for the input-output bound processes? So, but I would like to show you one more slide over here. Most of the students, that includes me, whenever we're given a task that is a group task, and it could be done with the help of parallel programming. We can do things parallelly. But this is the type of parallel programming that we end up doing. So we're there to support our friend morally, but there's actually just one person who's working around. So if we do it simultaneously, I think we can have a lot more better projects. So that's it. Thank you.